So they told me the rules for this talk, 2 slides, 8 minutes. I'm disobedient, so I have 17 slides, but you're not going to see all of them. You're just going to see the ones with the pictures. So I'm going to ask Sheldon to skip 1, skip 2, et cetera. I'm talking about this little circuit board that you have in your hands. It's a noise filter for switch mode power supplies. Why? Because switch mode power supplies are cheap, small, and safe in that you don't have to mess around with the semi-lethal mains voltages. Somebody else has already done that. Somebody else has gotten regulatory approval. You just pay $5 and you get it. They're great, except that they operate at pretty high frequencies and they spray digital noise onto the DC. And so what we're trying to do is to extract the DC and get rid of the noise. That's the purpose of this board. Okay, Sheldon, let's go until we see a blue picture. Keep going, keep going. There, up, back. All right, so what do we got? We've got a low pass filter. All that means is that in comes both DC and the unwanted noise. Out goes only DC without the unwanted noise. How do we get rid of the unwanted noise? We build a voltage divider. The inductor has 0 impedance at DC and infinite impedance at infinite frequency, and the capacitor is the opposite. Infinite impedance at DC and 0 impedance at high frequency. So when DC comes in, it gets shorted straight to the output, just exactly what we want. When AC comes in, it sees a high impedance here, so it says, oh, I can't really get there. And whatever does get there gets immediately shunted to ground by this very low impedance. Okay, so there we have a circuit with 2 electronic components, an inductor and a capacitor. When you see an inductor and a capacitor together, what do you think? You think, oh my God, it could resonate. So let's take a look and see what happens when you put an inductor and capacitor together. Next one, please. Oh, and look, it resonates. Oh, I'm sorry, go back. I forgot to tell you the names of these things. L1 and L2 and C1, those are kind of lame names. So for the inductor, I'm going to call him Lewis, and for the capacitor, I'm going to call her Camille. So let's see what happens when you put Lewis and Camille together. They resonate. And that ain't good. That means if you're unlucky enough to have this frequency coming out of your switch mode power supply, it actually doesn't get passed on to the output. It resonates and grows beyond the original amplitude. And the simulator says it can be as much as 40 dB tall. And that ain't good. What is good is the tremendous attenuation we get out of a single LC filter. But that's when the L and the C, when Lewis and Camille are ideal. Regrettably, you cannot buy ideal inductors and capacitors. And with more realistic circuit models of inductors and capacitors that you can actually buy, this is what happens. Lewis and Camille still do resonate together, but Camille has self-resonance and Lewis has self-resonance, and we don't get the attenuation that we wanted. In fact, we get this ugly stuff, and I'd like to get rid of that ugly stuff. So let's go to the next slide. Why does it have ugly stuff? Because Lewis isn't an inductor. Lewis is an inductor with some, it's made of copper wire, and copper wire has resistance. So this is the winding resistance of Lewis. And the individual coils themselves on the coil former have capacitance among them. So it's actually a 3-element circuit model. Same with the electrolytic capacitor. There's the capacitor. It has some internal resistance. That's called equivalent series resistance, or ESR. And it has some lead inductance. That's called ESL, equivalent series inductance. These are the values for this one particular Panasonic capacitor that I'm going to recommend you use when you build this board. So regrettably, a circuit that has 2 electronic components has 3 resonances. Doesn't that stink? So what are we going to do to get rid of the resonances of Lewis and Camille? We're going to add Ralph and Ruben. So let's go to the next slide. And one more. Okay, here's Ruben, here's Ralph. Ralph is in series with Lewis, and Ralph dampens the resonance caused by the Lewis and Camille resonating together. Ruben damps the self-resonance of the inductor. And we're lucky in that the Panasonic capacitor that I have selected has such a big equivalent series resistance that it damps its own resonance. So we don't need to specifically damp that resonance. It's already damped for us by this non-ideal capacitor, but you can buy it. Okay, let's go to the next picture. Ah, there we go. So I have told LT Spice to take 6 steps of the resistor Ralph and 6 steps of the resistor Reuben, and I just picked the one that looked nicest to me. I picked the smoothest. So up here, it looks to me like maybe the cyan curve is the smoothest, and over here, it looks to me like maybe interpolating halfway between cyan and red would be the smoothest. So those are the values that I chose. It turns out that the right value of Ralph to me that gives the smoothest response is 0.1 ohms, 100 milliohms. And the right value of Reuben that gives the damping that I like is 1.2 kilo ohms. And we get a nice smooth curve without resonances. I'll let you ponder this later. This is sort of advanced topic, but the capacitor turns into a resistor at suitably high frequencies because it's a capacitor in series with a resistance. Eventually, the capacitance reactance becomes lower than the resistance, and so that sets a floor on the impedance of the capacitor. So that's why it changes from 40 dB per decade to 20 dB per decade. I think it's 20 kilohertz. You're talking about this point here, right? Yeah, about 20 kilohertz. Okay, so this looks pretty good. I mean, at 100 kilohertz, which is a typical switch mode power supply frequency, we're getting about 55 dB of attenuation. And that's reasonably good. But what does Tim Allen say? I want more. So keep going. So let's put 3 of them in series. If 55 is good, then 3 times 55 is even better. So I know this is a messy looking slide, but don't be scared. This stuff here, that's just Lewis. Here's Reuben, here's Ralph. That's Camille. So that's one stage. It's Ralph, Reuben, Lewis, and Camille. The next stage is Ralph, Reuben, Lewis, and Camille. Third stage is Ralph, Reuben, Lewis, and Camille. They're all the same values. I didn't try and deal with interactions. I just blindly slapped it down and gave it a try. And let's look and see what the results are. It's pretty darn good. The resonances have been removed. The corners are relatively smooth. And here at 100 kilohertz, we're getting 160 dB of attenuation. That's 10 to the 8th power. I would think so. That reduces 1 millivolt to something small. And there you have it in your hands. Let's go on and look at the next slides. I know you can't read this, but there is a KiCad schematic. I put these things on the wall over here and here. If you want to, you can scan that with your phone and download the entire slide deck, including this in high resolution. Let's go to the next page. I said it was cheap. Here I put in all the components to make one of these boards at Mauser, and it says that's $7. I also put in stuff and asked Mauser how much to make 50 of these boards, and the answer was $3 a board. And if somebody wants to make even more than 50, like, I don't know, Dan Macy, it may come down even lower than $3 per board. So when I promised you cheap switch mode power supply filter, this is kind of my idea of what cheap means, okay? There's what the board looks like. You know what this looks like because you have it in your hands. This is what it looks like when it's assembled. Notice that I've made the board a little bigger in order to accommodate a greater variety of capacitors. So in the board in the store, it will only accept capacitors that are 10 millimeters in diameter. These that I've got on here are 12.5 millimeters in diameter, and you can see there's room for slightly bigger. And same with the length. You can see that on either end of the capacitor, there's a little room. So you have room to grow and shrink the capacitors, to put in the ones that are easy for you to buy, to put in ones with better specs than these if you want. I recommend the Panasonic ones, and the bill of materials, which is on the schematic, calls for the Panasonic capacitors, but you know, you do you, whatever you want. Okay, one more. And the entire slide deck, including the slides that we skipped, are online on my website. So if you scan this with your phone, or if you just type this into your phone, you'll get the full PowerPoint with all 16 slides. And that's it, I'm done. Was that 8 minutes?
That was fantastic, Mark.
Okay.
That was really good. Okay, so another power supply filter by Mark. And so the question that everybody or who has used one of your power supply filters is going to ask is, compared to the existing P089ZB, the first one you did, and then the surface mount version that's even better called Amy Alice, how is the performance of this from a objective standpoint?
Okay, I'm not going to answer that question. I'm going to expand that question.
Go right ahead.
What are the similarities and differences among those 3 boards? The first one, the ones in the store, has 2 stages instead of 3, but its downfall is that it uses very low value series resistors so that it can handle 3 amps from input to output. And it turns out that those very low value series resistors, they're actually current shunt resistors. They're hard to buy. They go out of stock very frequently. And so Tom Nadeau, who restocks the DIY store, is always begging me, please help me find another source for these because they're out of stock. So this one uses 0.1 ohm resistors, which you can buy everywhere, and they're not current sense resistors. So it's going to be easier to populate. This one is 3 stages rather than 2, so it's going to have better attenuation. Now, Amialis is a surface mount board, and some people, including, I'm sorry to say, me, have shaky hands and find surface mount difficult to deal with. And so some people either shy away from surface mount or absolutely refuse to deal with surface mount. So this one is explicitly through hole, as you can see with the board in your hand. So that's good if you really must have through hole. Amialis also uses parts that are only available in surface mount. It has these really tremendously good feed-through capacitors that the through-hole equivalents are not nearly as good. I mean, not nearly as good. Amialis also uses a ferrite bead, which is a mixed blessing. It gets tremendously good attenuation performance, so good that I don't know how to measure it. I don't know how to measure the attenuation performance of this, which is why I'm showing you simulation. But part of my goal is to get you excited about simulation. Look, we fooled around here and we got 160 dB of attenuation just by waving our hands and saying, Reuben, Ralph, Reuben. Wasn't that fun? That's going to be hard to do with Amialis. So, all 3 of them are good, but this one is the simplest and the cheapest.
How many amps, Mark?
Only 1 amp. Okay, good question. That's the most fundamental trade-off. If you look at your board, you'll see Filt 1A max. That's code. What that means is 1 ampere maximum. So that's how I was able to fit 3 stages in series, because I'm allowing myself enough series resistance where you can deal with that much voltage drop if it's 1 amps. You certainly couldn't deal with that much voltage drop if it were 3 amps. So the 1 amp maximum, this is for line stage applications, headphone amplifiers. This isn't, don't go putting this in your first watt, 20 watt Class A amplifier. It's not going to do it. But for your wall wart oriented phono pre, or yes, I said phono pre, I think you can do this and the noise will be so small that you can make a phono pre out of it. For your headphone amp, for your B1 Mesmerize, it's a good fit and it's cheap. And nobody else in the world has it but you.
Hang on, let me get this. And Amialis is good for 4, right?
Amialis is good for 3.
3.
So they're all good for 48 volts. Amialis and the one in the store are 3 amps. This is 1 amp.
Here, Steve's got a question.
Please.
Would you put more than one of these in parallel to get a higher current rating?
You could, but I think you'd have to be conservative and say, if 1 gives you 1 amp, 2 gives you 1.5, because they're not going to do perfectly equal current sharing. That Murphy's law is looking over your shoulder trying to give you a rectal drilling. And so I would be careful about that. I would downrate that.
Absolutely fantastic. The ever esteemed Mark Johnson, everyone.
Thank you.